Okay, this is Team Race Condition, giving the demonstration and the video for our wireless RC car system over Bluetooth.
I'm Zerind Spore.
I'm Gavin Harwood. I'm Jacob Halverson.
And I'm Dwyer.
Okay, this is Team Race Condition showing the demonstration of our first-person RC car system with wireless control.
All right, let's turn on the steering wheel.
Now let's turn on the car. We'll wait a moment for it to connect over Bluetooth.
Once it connects, there will be a chime, just like that.
There we go. Now we can showcase the pedals to make it go. And if I pick up the steering wheel here, we can turn it left, turn it right.
As you can see, the IMU is controlling the stepper motor that turns the car wheels.
Do you want to demonstrate the time of flight sensor?
Yep, so if it's driving on the ground, it's about to hit something, it automatically stops. You can see that the brake lights also turn on. And then once it's clear, you can keep going. And then if you hit the brake, that also stops, turns on the brake lights.
Can you get the brake in the shop for that?
And in reverse, we have it chime to signify that it's in reverse.
And you can see that the time of flight sensor doesn't do anything because you want to be able to back away from objects that you're about to run into.
You can also steer while going forward.
In addition, we have a few minor features added on the car, such as the horn.
So we turn the horn on.
As well as a headlight switch.
And they're pretty dim, but
Yeah.
they're turned on up there.
The final added feature, which was not implemented by us, includes a GoPro on the front, which we have live streaming to give a better first-person view of the car system.
And then when you disconnect it, it'll...
The controller's not been turned on. Often takes a few seconds.
And it takes a few seconds so that if we lose communication temporarily, it won't just immediately give up. It would be able to fix itself if we can reestablish a connection. All right.
And that should conclude the demonstration of our RC car wireless system.
Yeah. This is a live demonstration of the car. Do you want to drive into my foot? Yeah.
So this is a system overview of our Capstone project. Essentially, we created a first-person view, remote-controlled vehicle
We custom designed the PCBs and prototyped a remote, as well as connected different pedals to our steering wheel PCB.
In order to achieve connectivity, we established wireless BLE communication between two PSOC-6 microcontrollers, which gives us responsive handling and is able to implement a comprehensive package system.
Then to get that immersive driver experience, we use an IMU, which is integrated into the steering wheel, as well as potentiometers for both throttle and brake control. And this drives the steering system, which uses a stepper motor and a potentiometer to mimic a servo.
For vehicle actuation and sensing, we used a couple components, including a brushed PWM controlled DC motor for the speed, stepper motor for steering, and a time-of-flight sensor for real-time collision detection.
And we also had battery power to give battery management systems on both the vehicle and the remote control, so they do not need to be plugged in.
All right, I was responsible for the time of flight sensor integration. This is used for collision detection, and you can see the time of flight sensor on the front of the car. Then I also integrated the IMU to detect when the steering wheel is being turned, as well as integrated this with the steering system that's on the car, where we use a stepper motor as well as a potentiometer to act like a servo based on how far the IMU is turned. I already mentioned the automated collision avoidance, that was with the time of flight sensor. And then I also added some different graceful failure software. So for example, if the IMU hardware fails, then it won't freeze up the whole system, and the same idea was integrated with the time of flight sensor. And then I also fully prototyped and designed the physical car, from the gears to the wheels to the main body itself.
All right, so my main responsibilities involved most of the speed and acceleration control. So first of all, the DC motor driver, which actually drives the back wheels of the car and causes it to accelerate and slow down. Then moving on to the pedal potentiometer circuit, which is attached to our physical pedals and uses the Sci-Hel ADC sampling software from the PSOCs, and then adding a second one as well so that we can have gas and brake with software for the braking to actually override the gas pedal and the speed control. Then moving on to the car speed integration, where I actually integrated the software for the pedal potentiometers and the DC motor to control the speed and acceleration at the same time, sent over the microcontroller BLE, and then sent to the DC motor queue. That was my main electrical components. And then I also participated with the design of the 3D steering wheel and the pedals. And then at the very end, when we're integrating everything together, updating the pins and the custom PCBs together with the logic for some of the smaller added components like the switches, that control some of the minor features of the car.
My contribution to the project really consisted of finalizing the remote control PCB. So essentially I integrated the IMU circuit, the power management circuit for the batteries, as well as the pedals, as well as incorporated an external header for the RF transmitter, which did not end up making it into our final project. Additionally, this remote control PCB incorporates a PSOC-6 to communicate with the various circuits and digital pins to send directions to our car. Aside from that, I also focused on the RF system, which did not end up being incorporated into our final project. This consisted of the RF transmitter PCB. Essentially, this modulates a baseband BPSK signal up to 433 megahertz and wirelessly transmits it. This included a few different RF components and submodules that I designed. This included a DAC, an LNA, PA, as well as software for this system as well, including a 3RTOS task to run BPSK on this. Aside from the RF system and the remote control PCB, I also helped with general debugging for the car PCB as well, and diagnosing different hardware and software problems.
All right, so probably my biggest contribution to the project was integrating BLE. So I developed an integrated low latency packet system and set up the GATT communication between the remote control and the car, and then helped integrate all the different tasks into that system. I also did a lot of integration of the cardboard hardware. So I integrated all the car peripherals and designed the PCB, which integrated like the stepper motor with the potentiometer, and then also added in the DC motor to drive the car and some of the peripherals like the horn and the headlights. I also designed the power supply circuitry used in both the car and the remote control. That was a tricky task, but ultimately we got pretty stable reference voltages at 5 volts, 5.4 volts, 3.3 volts, and the battery, which directly drives the motors. As mentioned earlier, I developed the stepper motor circuitry for the stepper motor driver, and I also worked on some of the RF board stuff that we ended up not using. I designed the transmitter, the mixer, or the receiver, the mixer, the oscillator, and the filters.
We really enjoyed this project and learned a lot along the way.
Thank you, Joe Krachey.